We're about to look at sample variance and sample standard deviation, but it can be quite confusing because there's already population variance and there was already population standard deviation. And so we just want to take a quick moment and show you the notation here. We've got population variance, or sigma squared, population standard deviation, or sigma. That's when we're working with all the data. And then in the far more realistic case that we're not working with all the data, we're just working with a hopefully representative sample, we've got sample variance, S squared, not sigma squared, but S squared, and sample standard deviation, not sigma, but S. In practice, this is probably the value that matters the most to us, that we are going to come across the most, is probably the better way of putting it. Let's see how to get there. Earlier, we looked at this billionaires data and we assumed that somehow Forbes had access to all of the tax returns of all these people living in each of these individual countries, or they were somehow able to take out the net effect and get all of this data. And maybe that's true. But maybe it's not true. And maybe when Forbes got this data, they got it on the basis of a sample. And hopefully it was a sample that was obtained in an ethical manner and also in a representative manner. But for now, what we're going to assume is that even though we're dealing with all of the same data, we are not going to assume that we have all of the data. Okay, so how does that change our calculations? And the answer is it does not change our calculations very much for calculating a sample variance or a sample standard deviation. There's one tweak that we have to make. So we're going to go about starting off with the same way that we did before. We're just going to take equals average and get 2.37, and the 2.37 here is equals $C, $27, and that gets us a whole column of averages. We get our individual deviations. Notice that we're now, instead of saying our observations x sub I minus mu, the true population mean, we're subtracting x bar, our sample mean, which is all that we have. And over here, we're doing the same thing. We're squaring the deviation, but squaring the deviation not from the true population mean, but from X bar. So we go through, everything is looking the same. If I just take the sum here and go up, what we'll find is that it's 0, the way that it's always been. So that's good. We're going to take a sum of the squared deviations from the sample mean, and we get 89.88. That's the same as what we had when we assumed that all this data was working with a population as opposed to a sample from the population. Here's where things get different. We had 22 total values, and when we assumed that we were working with the population, we had all the data, then each one of those data values was an independent data point. But when we're dealing with the sample, what we're doing, notice we used a sample metric in order to generate another sample metric. It's like making a copy of a copy of a copy. And so the number of independent data points goes down. It goes down from 22 down to 21. That's where those degrees of freedom come in. So instead of the 22 sample size that we're going to divide by, like when we normally take an average, divide by the number of data points, it's divide by the number of independently determinable values. And that, in this case, is not 22, but 21. And so we are going to divide our values, and we get 4.2799 as the sample variance. And to go from sample variance to sample standard deviation, we just do SQRT equals SQRT, and we take the square root of the sample variance. So we'll come up with 2.0688 as our value. Let's see what happens here if I just calculate variance. Now, before I had to do like var.p and then calculate the arrange or standdev.p, but these spreadsheets like Google Sheets or Excel, they assume you're working with a sample. So you can just put in the values like equals var. Don't worry about like a .p. You can put .s if you really want to, but you don't have to. Just var and equals var, and we come up with 4.28, which is the rounded version of what we saw over here. And if I take equals stdev, standev, and of the same array, I come up with 2.068, which is that same value. So really the only difference from a calculation standpoint is that you divide not by n, but you divide by n minus 1 when you're dealing with a sample standard deviation or sample variance as opposed to a population standard deviation or variance.